Hey everybody, I'm Andy. Today I'd like to talk about some of our recent work in vision-based manipulation. And in the spirit of retrospectives, this talk will be more about the challenges that remain and where I think more work could be done. So today I wanted to walk us through a simple example and use it as a way to discuss some of today's manipulation challenges. So to start out, imagine a task where the goal is to pick up the red block and put it into a fixture. This is what it would look like if the robot was successfully doing it, in this case with a suction cup gripper. And because we're doing vision-based manipulation, we want to effectively do this from images, right? So let's just say that this top-down view here is our input image. So then, a hard-nosed roboticist might be like, we already know how to do this, We just use pose estimation, very easy. And at first glance, you might be like, oh yeah, I guess that makes sense. So then we define canonical poses for the objects in the scene, one for the block and one for the fixture. And then you go back to your computer and you design a pose estimation algorithm that predicts the poses from images. And since it's 2020, what better way to do that than with neural nets, right? So then we slap on a convolutional network and tweak the architecture a bit so that it could better fit with our pose estimation pipeline. This was essentially what we tried to do for the Amazon picking challenge a few years ago, where we essentially used convolutional networks to predict segmentation masks for the objects. And then we'd align the masks to their 3D object models to get a 6D pose. Since then, there have been many follow-up works that have come up with much more elegant architectures than what we had for doing this. In some ways, this is great, especially if you're in a structured setting where you know beforehand all of the rigid objects that you'd be manipulating. But then, as you collect training data for your model, you might start to realize that not everything in the world has a canonical pose. So, for example, articulated objects like a laptop, does that mean that there's a separate pose for each moving part of the laptop? What about deformable objects like a t-shirt? How do we define poses for that? One possibility is to treat it as an infinitely articulated object and then associate visual descriptors to different parts of the t-shirt, which might work. But then what about uncountable piles of stuff? Are we going to detect poses for each individual coffee bean there? And then what about fluids? Would it have a canonical pose? And if you've never seen these objects before, how do we generalize pose estimation to unseen objects? This seems critical if we plan to build, for example, trash cleaning robots or debris clearing for disaster response scenarios. The challenge with pose estimation is that it is very much tied to what we define as known rigid body objects in the world. So if we took a step back to think about a vision method that might scale to the complexity of the real world, I think there is a case here for end-to-end learning, where instead of mapping from images to poses and then poses to actions with a planner, you just directly map from images to actions. To illustrate why this is interesting, let's come back to our simple example and suppose that the way we've parameterized our actions is with a picking pose tPick and a placing pose tPlace for the suction cup gripper, where an example could be suctioning one leg of the L-shaped block and then placing it into its corresponding location in the fixture. Suction, by the way, is actually very commonly used in industry for grasping. With a single point contact, it's quite simple and very robust. It can't grasp everything, but it can do a lot. Anyways, the important part here is that this formulation doesn't make any assumptions of objectness, meaning that we don't assume an explicit definition for what an object is. And that actually leads to some nice benefits. For example, in this task, there are other low-level visual cues that the robot can learn that might enable it to succeed just as well. um, like that corners match to corners, uh, or that edges align with edges. And the cool part is that these features might actually be more generalizable to new scenarios. Um, so for example, if suddenly our object and fixture both grew bigger in size, then these features could still apply. Or if we had different shapes of objects, they could potentially still apply as well. So I think rather than thinking about vision as a bunch of poses, we could instead learn how to match these low-level features, for example, between the block and the fixture. And that actually gives us an opportunity to generalize and scale to new tasks without having to define canonical poses for each object category and capture 3D CAD models or collect object-specific training data. So we touched on this idea in our recent work called Form to Fit. And the key idea was that for assembly tasks, which involve inserting objects into corresponding holes in a kit, you could essentially learn generalizable vision-based pick-and-place policies by formulating the problem as a shape matching problem, and then tackling that by learning local visual shape descriptors. And so in this case, we make a pixel-wise prediction of shape descriptors and then use that to match picking actions to placing actions. So here's a visualization of the learned descriptors projected into color space. And you would see is that what you would see is that different parts of the same object would match to different parts of the placement location that it would be fit into. So intuitively, you can think of this as learning the general concept of how things fit together, which is quite powerful in the context of industrial assembly tasks. So in this work, we showed that using generalizable shape descriptors allows us to assemble unseen kits with new objects. But one of the remaining challenges is that the descriptors here are actually pretty hard to train because each pixel is responsible for capturing the local geometry around that point. And that unfortunately takes a lot of data to learn and parameter tuning to get right. So we're now looking into ways in which we can improve that. This project was led by Kevin Zaka, who's now studying at Stanford. But zooming back out, if we look at all of this from a data-driven perspective, I think the two modern formulations for pose estimation and end-to-end are incredibly similar. We're essentially trying to train a high-capacity model to map from images to some compact group that could either be poses or actions. But I think that what distinguishes the two the most is that with pose estimation, there's usually a one-to-one correspondence between poses and the objects that you see. Whereas with actions, you could potentially have a very complex distribution that you're trying to model. So in other words, in pose estimation, you typically only have one right answer. But then with end-to-end learning, there can be many right answers. And I think fundamentally, that's what makes end-to-end learning so hard, regardless of what kind of function approximator you're using. So we can actually get a start. So we can actually start to get a feel for this if we go back to our simple example where we'd like to train an end-to-end model for this task. The thing to recognize here is that the set of successful picking poses is effectively a distribution, and it might look something like this. If we visualize it as a heat map, then the set of successful picks would basically cover the surface of the object. This would be successful picks with a suction cup. We want our end effector picking pose T-pick to be sampled from this distribution. The challenge for our model here is then, how can we recover this distribution with high accuracy and fidelity? And this is actually a tricky problem. Even in just a simple grasping with the suction cup setting, these distributions can actually get pretty complex depending on the shape of the objects or the physics of the suction cup. For example, here we draw a few object shapes with the distribution of successful suction grasps overlaid on top in red. It can be highly multimodal in nature, depending on the number of objects that are in the scene. It can be oddly shaped, highly non-isotropic. Imagine if you were trying to grasp a donut, the distribution might follow the contour of the object, or maybe sometimes not because of suction physics, and some part of the object might be too thin or maybe porous. Keep in mind that I've drawn these distributions with clean edges between the red and the gray, but usually these boundaries are much smoother and noisier than this, with some randomness because of physics. So then also depending on your embodiment or your end effector, for example, if it was just two-finger grasping, then the distribution of successful grasps can become even more complex, maybe multimodal on different parts of the same object due to symmetries, or in the case of the donut, the distribution is effectively spiral shaped through the space of SE2 as the gripper sort of follows the ring of the donut. So the vision-based grasping problem is essentially how can we recover these distributions from images? And sort of the beauty of vision-based manipulation is that the structure of the visual data can provide us with amazing priors for learning this. So for example, that say because of some particular embodiment or a specific setting, your ground truth distribution looks something crazy like this. Um, like you could totally try to train a blind implicit function with regression to memorize this distribution. And then you would need a bunch of data samples, both positives and negatives, to be able to carve this out of thin air to fit the function. But it's just a heck of a lot easier if your input data just look like this. And now suddenly you've got an input bias that helps you a lot. And maybe with just two data samples, you can already figure out what lies on the object is good, what does not is bad, and then you can learn to fit the function a lot more efficiently. So the main idea here is that it's easier to learn these distributions if they are spatially and directly anchored on things like visual features in the images, like the shapes and the boundaries of objects, because they can provide very helpful inductive biases. And also so that you could essentially leverage equivariance here to exploit symmetries in the data. Uh, these are the things that I think from a data representation perspective can make end-to-end models learn more efficiently and better generalize. So then how do we implement this in practice? Uh, Luckily for us, this problem formulation is quite similar to the image segmentation stuff that computer vision people have recently made incredible progress on, where your input is an image and your output is a dense prediction with a one-to-one pixel correspondence to the input. And the key aspect here is that the network is fully convolutional, which means that every layer is a convolutional layer, so that equivariance is preserved, where every pixel in the output corresponds to a decision being made with respect to a chunk of pixels in the input. And that as you translate over the output, you're effectively translating over the input as well. So then we can use these same mechanics to give us a dense prediction of the spatial distribution of successful grasps. And we call these affordance predictions, inspired by Gibson's work in psychology. Essentially, we're modeling a value function per pixel action that corresponds or correlates with picking success. And in this particular case, this is with the suction cup. And this is essentially what we did to win the stowing task at the Amazon Picking Challenge in 2017, which was the second time that we participated together as Team MIT Princeton, where we were the only team to have a system that could successfully grasp all of the new objects that Amazon had in this version of the competition. And the way that we collected training data for this was by going on a shopping spree at Target and buying over 200 different items to train the robot to grasp them. This system worked quite well, but it was clear over time, however, that it also had its shortcomings. So, for example, in order to properly leverage the spatial biases that I was talking about, both the actions and the input data have to live in the same space. And so there becomes this sort of mismatch problem where our action space lives in this higher dimensional SE3 space, but then our input images are still two-dimensional. So then the extent to which you can leverage spatial biases and equivariance becomes limited. What we did in the picking challenge to compensate was to resolve some of this ambiguity by using the depth data that we get from the sensor, as well as computing some surface normals. But I think that this is far from a real solution, because then you have issues of camera perspective, where, for example, you only have a partial observation of the scene, and as a result, you can't predict grasps for the occluded regions. So I think that this is a good case for where 3D vision could come in and save the day. Uh, what's the best way to leverage that? I think still remains a relatively open research question. And I'm not sure, but I think that's a very promising direction. And another thing is that to pick something up is a relatively single step task, but grasping is usually always just a means to an end. And so the distribution of actions that you take thereafter are typically conditioned on the actions that you took beforehand, and also vice versa. So if we go back to our simple pick and place example, it's quite clear that if we change the location of our initial pick, then our distribution of successful placing actions would also change. Here's another example with Towers of Hanoi, which is a famous puzzle and coding interview question where the task is to pick and place 3 disks from one tower to the third tower. But the trick here is to do it so that the larger disks are never placed on top of smaller disks. If we look at the distribution of placing actions at each time step, you can see that given this particular initial picking location, the distribution of placing location actually follows a spiral shape in SE2. Here we project that spiral and visualize it as a colored ring, where each color represents a different rotation. And as you can see that as we follow the ring, we also have to rotate and translate the end effector respectively to successfully place the ring onto the peg. So then how exactly do we learn these types of distributions that result in complex sequential manipulation behaviors like this? I'm not quite sure yet, but we're working on it. But what I do know is that anchoring these distributions on top of visual data to exploit the spatial biases underneath would certainly be very helpful in learning this. And not only for pick and place, but lots of manipulation tasks are sequential and dynamic by nature. So once you add in the dimension of time, then suddenly your distribution of successful actions becomes this higher dimensional shape that lives through space-time, and each part of the shape weaves through as you do time-dependent tasks, branching off in different ways or separating into pieces and different modes. Uh, but even then, I think that there's plenty of upside to be gained by conditioning those action distributions directly on the visual input. Because then the spatial structure there could provide us with useful biases as a means to more quickly learn the distribution of good actions. And here, for simplicity, I've drawn each input image as a slice of this space. But you could imagine a one-dimensional grasping action space where the best grasp translates with the object as it moves back and forth on the conveyor belt. One thing to keep in mind, though, is that most of this has only been explored in end-to-end models with spatial action spaces. There are other sensing modalities and types of action spaces like forces and torques, and I think it's still unclear how we can apply geometric spatial biases here. But I do think that a key part in enabling that could be connecting it via physics. And I think that that would be a really interesting area for research. So to summarize, here are a few takeaways. I started off by talking about pose estimation and discussed how it is still limited by what our definition of an object is, and hence remains an open research question. So I started talking about how it might make sense to rely more on low-level visual features to do vision for manipulation. And one of the things that makes end-to-end learning attractive for this is that it can make better use of these low-level features to learn more generalizable policies. I then gave examples in the context of a simple block insertion task and also described how we applied these ideas in our recent work on learning generalizable assembly with form to fit, where I think one of the remaining challenges is to make the learning of the visual shape descriptors less data efficient, less data intensive, excuse me. Let's just redo this takeaway section. Where one of the remaining challenges is to make learning the visual shape descriptors less data intensive. I then talked about some of the challenges behind vision to action, and that it is hard because our actions can come from these highly complex distributions. And so there are many right answers. I then discussed that how the learning can be made easier by better corresponding spatial cues to actions. And I talked about that in the context of learning grasping in the Amazon picking challenge, as well as a placing example with a simple Towers of Hanoi task, which illustrates how complex the problem can be. And finally, by leveraging the spatial structure of visual data, I believe we'll be able to get faster learners. And we've been exploring this in various applications, including pick and place reinforcement learning and mobile navigation, which I wasn't able to get into the details of in this talk, but you can learn more about that by following the project links in my webpage. And that concludes my talk. Hope you learned something useful that you can apply to your own work. And last but not least, I'd like to thank my collaborators and co-authors with whom I've spent countless hours discussing these ideas. And that's it. Thanks for listening.